So in this lesson, we're going to look at using integrals to find area. We've already done that. We've worked with concepts of area from the beginning of the year. But now we'll review how the integral from 0 to 2 of x squared dx equals the area under the curve. And another concept that's being used here is we're dividing up the area into an infinite number of intervals that make these rectangles. Here's an x interval that is the base of a rectangle, and we're filling up the space with an infinite number of rectangles. That's how an integral works. And all we're going to add today is that we don't just have to find the area between the graph and the x-axis. We can find the area between two graphs, and it's just going to be, so if we're still going to 2, 0 to 2, and we're just going to take the top curve minus the bottom curve. So in this problem it would be x squared minus x if we were trying to find the area that ends at 2. So that would give us this area here. All right, so let's visualize what's happening here. The graph is shifted up. It's the area between the graph, the x-axis, and the lines -1 and 1. So we want to find that area. So the first step is to decide, should we use vertical or horizontal rectangles? Up here we saw how an integral is the sum of the areas of these vertical rectangles, and the width of a rectangle is the differential of x dx. So there's the width of a rectangle, that's the height of a rectangle, and that's a little bit of how area is calculated with an integral. The sum of base times height. So we want to have rectangles that always touch the same lines. So if I drew a horizontal rectangle, we have this, this, this. So when I draw a horizontal rectangle, this rectangle touches the same two lines. But then when I draw this rectangle and this rectangle, now it's touching different parts of the line. So in this graph, it's better to use vertical rectangles because every vertical rectangle will have this graph as the top and this graph as the bottom. So we want to use vertical rectangles, and that means we're looking at dx. This tells us that we have to have our integral in terms of x. So now we need to find x interval. The x interval of the region. Well, that's easy to see in this one. It goes from -1 to 1. And then we just find the area from -1 to 1. And that's going to be top curve minus the bottom curve is y equals 0. And just so that we get used to the process, we'll put a 0 there, even though you wouldn't need to put it there. Alright, so now we can do the antiderivative, x cubed over 3 plus 2x, negative 1 to 1. And that'll be 1/3 plus 2 minus, put in negative 1 in there, it's negative 1/3, and minus 2. So that'll be 1/3 plus 1/3 is 2/3, 2 plus 2 is 4, 4 and 2/3. Alright, so go through the 3 steps and try to find the area of this region. Pause the video. Here we have a reflected parabola, and here is a reflected radical function. So we're going like that, and we want to find the area between the curves. So should we use vertical or horizontal rectangles? In this case it wouldn't matter, but since we're so used to doing things in terms of x, always use vertical if you have the choice. And that means if you have a vertical rectangle, you have dx. Everything will be in terms of x. Okay, we need an x interval. If that were a dy, then we'd use a y interval. So we need the x interval of the region. We need to find out where that region ends. And we do that by solving for the intersection. So divide by a negative, square it, so x equals 0 and x equals 1. We know that the intersection is at 1. And step 3 is find the area from 0 to 1. And we're going to do top minus the bottom. Alright, the top curve is the parabola, and the bottom curve is the radical. And we'll have this is x to the 1/2. Remember that radical is x to the 1/2, so we're going to add 1 and then divide. We have negative x cubed over 3. This will be plus x to the 1/2, sorry, 3/2, because it started out as a 1/2 and we have to add 1 to it, so we'll get 3/2. And we're going to evaluate it from 0 to 1. So if we put a 1 here, that'll be 1 cubed is 1, negative 1/3. Put a 1 there, that's 1. And we'll just write this as the reciprocal because we're dividing by 3/2, so that'll be 2/3. And when we put a 0 in these, we get 0. So 2/3 minus 1/3. And the area is 1/3. All right, and pause the video and try this one. We know it's a parabola shifted up 1, and it has the other line is at 3. So again, we could use horizontal or vertical rectangles, but it'll be easier to use vertical rectangles. So we're using vertical rectangles. Means we have a dx. That x tells us we need an x interval. We need the interval where the region starts, x interval from where it starts to where it ends, and that is with the intersection. The intersection of these will give us the interval 3 minus 1, positive or negative radical 2. So the interval goes from negative radical 2 to positive radical 2. And then we integrate from negative radical 2 to positive radical 2. And we're going to do top curve minus the bottom curve. The top curve is 3. The bottom curve is x squared plus 1. And we'll do the, let's simplify it first. So 3 minus 1 is 2. 2 minus x squared. Now anti-differentiate, so the antiderivative of 2 is 2x. X squared is x cubed over 3 from negative radical 2 to radical 2. Substitute the radical 2 in. And we'll have that. When we cube the radical 2, you could think of it as this. Cubing the 2 gives you that. So really, we could write this as 2 radical 2. This becomes 2 radical 2. All right, let's check what's happening there. Put the radical 2 in there, and if we cube the 2, it'll look like this, and we'll take a 2 out in front. Oh, and it's over 3. That's what was wrong. All right. Over here, we're going to have a plus 2 radical 2. Now, cubing the negative makes it negative, which makes this positive, and that makes it negative. So we have the same thing happening here, 2 radical 2 over 3. So we'll have 4 radical 2 minus 4 radical 2 over 3. And this would be 12 radical 2 over 3 minus 4 radical 2 over 3. We get 8 radical 2 over 3. So this is just a matter of drawing all these straight lines and finding the region. Y equals x, x equals 1, and x equals 2, and then y equals negative 2. We need the region bounded by all of these lines, so I wouldn't say it's the triangle because it's not bounded by that, and it'll turn out that it's going to be that region. So we look for vertical rectangles, reminding us that it's a dx, and that means we need the x interval. The x interval here we can just see it's from 1 to 2, and then we integrate from 1 to 2, top minus bottom. The top is x and the bottom is negative 2. So we'll have x squared over 2, that'll be plus 2x. And substitute the 2, we'll have 2 squared, 4 over 2, and then 2 times 2, 4, minus 1 over 2, plus 2, alright, so that's going to be 2 plus 4 is 6, minus a half, minus 2, and it's 4 minus a half, 3 and a half. All right, last example. Pause the video and try this one. We have negative 2x, x equals negative 4, x equals negative 1, and y equals 10. So we want the region bounded by all of these lines. We have 4 lines, 1, 2, 3, 4, so it's going to be that region. And can we use vertical rectangles? Yes. So vertical rectangles, that means we want an x interval. We see the x interval from negative 4 to negative 1. And then integrate from negative 4 to negative 1, top minus bottom. The top is 10, the bottom is negative 2x. So we have 10x plus 2x squared over 2. So that'll be a 1, and we have a negative 10. Put the negative 1 there. Negative 1 squared is 1/2. And then we'll put in the negative 4. That'll be 16. Got a mistake here. It's not a half. Put the negative 1 there and we get a 1. Put in negative 4, we get negative 40. That's a 16. So negative 10 plus 1, negative 9 plus 40 minus 16. And that will be 15, because we'll get 31 minus 16 is 15. And we'll stop there.